Hey guys, welcome to my weekly series on me trying to record YouTube videos of the things that we would have covered anyway, just in case, you're struggling to get out of bed one particular morning and you can't quite make it to class. You can watch these YouTube videos and hopefully I will help catch you up. Today we're going to talk a bit about reaction pathways. So one of the most common questions that students ask me whenever I say I'm a chemistry teacher is, can you make meth? Well, technically, yeah. I understand how reaction pathways work. But the thing is, this is the science behind it. So this is chemical properties of organic compounds, and, well, the properties of an organic compound are largely determined by the functional groups, and all members of a homologous series generally undergo the same types of reactions. Basically, if it has a certain type of functional group, it will undergo the same kind of reaction. So let's kick it off. Alright, alkanes. So alkanes are super stable. They only undergo a few chemical reactions. Most obvious one is combustion, the one we've already covered this year. They readily burn an oxygen in an exothermic reaction, producing carbon dioxide and water. Question for the class: what's the difference between complete and incomplete combustion? Well, complete combustion will produce carbon dioxide and water. Incomplete combustion will produce carbon monoxide and water. Basically, if you blow out a match and you see black smoke continuing to rise, that's what's known as incomplete combustion. Complete combustion will display no such particulate. Here we have a little bit of a chem file about burning ice. Now, one of the things is water molecules bond very, very strongly, but they also bond kind of weirdly. It's the fact that you can actually store things inside ice. Basically, when it comes to global warming, we are going to hit a point where the ice starts to melt. And once the ice starts to melt, it frees the chemicals that have been trapped inside the ice, which will continue to heat up the Earth, which will continue to melt more ice, which will continue to heat the Earth, etc., on and on, so on forth and so forth. And look, we're going to hit a point, and it's probably going to be sooner than any of us would rather like, where we can't go back. And it's going to be sad and terrifying. Reactions of alkanes. The second thing we can do is something called a substitution reaction, and it's literally in the name. A substitution reaction involves replacing an atom with another element or group. Saturated hydrocarbons undergo substitution reactions with halogens to produce haloalkanes. So the reaction must be initiated by UV light. Here we've got chlorine, which is our halogen, and it reacts under UV light to form chloromethane and hydrochloric gas, which is terrifying thought. As the reaction proceeds, further hydrogen atoms can be replaced with different groups, and we can basically replace all of the hydrogens if we feel so inclined. The products will have different boiling points, so we can actually separate them by fractional distillation, which is really cool. But here we've got methane plus chlorine, UV light, chloromethane, hydrochloric. But we could take chloromethane, add more chlorine, and add more UV light, and we get dichloromethane and hydrochloric gas. And then dichloromethane plus more chlorine plus more UV light gives us trichloromethane and hydrochloric gas. Followed by tetrachloromethane, plus chlorine gas and UV light gives us tetrachloromethane. I think trichloromethane is the chemical formula for chloroform, but don't ask how I know that. Okay, reactions of haloalkanes. So if we have a alkane with a halogen attached, it can also undergo substitution reactions. It can undergo substitution reactions with electron-loving species such as hydroxide ions or ammonia. Because of the large electronegativity difference, basically this is strongly electrophilic, this is not. It gives a carbon a slight positive change, which means we can create methanol by just chlorinating it first. This is a big point, and I would write it down in your notebook. So the carbon atom can get attacked by negatively charged species, and it creates a little bit of a substitution reaction. OH in, Cl out. Cl out. Alright. This can also be written as RCl plus OH minus gives us ROH. It is also possible for a haloalkane to undergo a substitution reaction with water, but this is a slow reaction that requires a catalyst. So we've got chloroethane plus OH plus a catalyst. It gives us ethanol plus hydrochloric. I think common catalysts for this are nitrogen, and sometimes this also has to undergo or occur in the presence of sulfuric acid, making it a particularly complex and difficult reaction to separate. So we also have ammonia can attack positive carbon atom to form amines. Cl out, NH2 in, or here, Cl out, NH2 in. Doesn't really matter where it is. Reactions of alkenes. So alkenes are slightly different to alkanes in that the heck is more reactive. This is what we call an addition reaction. Addition reactions only occur where there's a double bond in between the carbons. Here, we break that in half, we snap that down the middle, and we're left with bromoethane, where we've stuck a hydrogen on this carbon and a bromine on this carbon. So during addition reactions, two reactants can become one product, double bond is destroyed, and atoms end up on both carbons of the double bond. If you give me a carbon with 5 bonds, I will publicly execute you. Of course I am not going to publicly execute you, but I will be very disappointed. Alkenes react with hydrogen gas in the presence of a metal catalyst to lower the activation energy requirements. So basically we need nickel. This is known as a hydrogenation reaction. This is possible due to the fact that ethane is a naturally occurring gas that we can use to turn into ethane. Alkenes react with halogens to form disubstituted haloalkanes. So here, break it in half, got, oh look, 2 bromines. If by any chance you wanted to put a bromine on the end here, maybe your best bet is actually to create this and then to chlorinate it. So the reaction with bromine occurs readily at room temperature without a catalyst, and it's used to test for carbon-carbon double bonds. It decolorizes as bromine adds to the double bond. So here we've got aqueous bromine and an alkene, and then it just disappears. Likewise, the color disappears here. Oh, that's actually alkane, sorry, my bad. So, alkenes react with hydrogen halides such as hydrochloric acid in addition reactions, as we've spoken here. I was going to talk about cis and trans isomers, but we don't have to do that this year, thank God. Okay. However, with this reaction, 2 products are possible. So we've got hydrochloric, right? Now, when we break this, there's going to be a spare positive charge there and there. And these are going to bond there and there. So we're going to have either 2 chlorobutane or 1 chlorobutane, because the hydrogen can end up on that carbon or it can end up on that carbon. Likewise, the chlorine can end up on the reverse carbon to wherever the hydrogen is. Alkenes can also react with water under specific conditions to produce alcohols. This is called a hydration reaction. As it turns out, adding more water to something hydrates it. This requires a phosphoric acid catalyst and 300 degrees Celsius to make it happen. Now, third type of reaction for an alkene is an addition polymerization reaction. So, alkenes can react with each other to form polymers in addition polymerization reactions. Thousands of monomer units are often used to make a polymer. So here we have vinyl chloride, and then you separate it by breaking the double bond, and it finds another vinyl chloride which has also had its double bond broken, and you get polyvinyl chloride, PVC, which is what it's made up in pipes. So here, write the chemical reaction for producing polyethylene from ethane. I'm going to pause it for a sec. I'm going to stop talking for a sec. You should probably pause it and give this one a go. If you want, feel free to reverse back to the previous slide. Oh. There. And take a look at how this is written with vinyl chloride, with the chloroethane, and polyvinyl chloride. Now I'll return back. Alright, I'm going to keep going. This is what it looks like. So we have ethane, double bond breaks, and we sort of have a little bond that indicates that it is bonded to something, and then just a bracket and an arbitrary end. This just indicates that we've got a lot of ethane molecules bonded together. Alright, try this one. Write the chemical reaction for producing polybutane from butane. Pause the video now. Alright, so here we've got polybutane. You'll notice that whilst this is a CCCC, the only way that this sort of works is if you have the double bond across the second. And you get a repeating molecule that looks like the one next to it. Have a look at margarine. So the raw materials used to make margarines include vegetable oils, but they're liquids, so they can't be spread the same way as butter. They contain long hydrocarbon chains that are polyunsaturated. So it's got multiple double bonds between carbons. So if you look over here, this is a double bond, this is double bond, this is double bond, this is double bond, this is double bond. So what we need to do essentially is to remove a bunch of these double bonds, so that way it will actually become saturated and turn into a solid. So to take vegetable oil and make it into margarine, we actually have to hydrogenate it. This is the act of taking hydrogens and putting these vegetable oils across a nickel catalyst. And as soon as some of those double bonds uncrinkle out, that's a very scientific word there, uncrinkle. This becomes thicker and actually spreadable. Alright, reactions of alcohols. So hydrogen bonding in alcohol makes it a very different molecule. Because the OH exists, it makes it quite strongly polar. So it's a liquid at room temperature and is soluble in water, and alcohols are often used as a solvent in cosmetics, pharmaceuticals, and my problems. It acts as a depressant in the human body and blocks the production of certain hormones, and it increases your chance of dying from a wide range of cancers and causes a lot of social harm in Australia. Boy, I wish I hadn't made that joke earlier. So, combustion reactions. Here is a practice question for you where you write the combustion reaction for ethanol in plentiful oxygen. So here we've got, I'm going to go through this with you. So we have C2H 5 OH. You can tell I'm not very used to drawing on this. I should buy a stylus. And we got a lot of O2 somewhere. and it forms CO2 and H2O. Now, pause the video if you want to balance this yourself. I'm going to give you 10 seconds to pause it. Alright, now, first thing as always, what we do is we balance our carbons. So we have 2 here, 1 here. We're going to put a 2 here. Now our carbons are balanced. H5 plus H is 6H. We've got water molecules over this side. So if we've got 6 here, we're going to need 3 here. So this is 3. Now what we need to do is count up our oxygens. So we have 2 times 2, which is 4, and 3 times 1, which is 7. So we have 7 here. Now normally we do the 7 over 2 and then multiply the whole thing by 2 and you get ugly. But because this is ethanol, we can actually subtract 1. So we've got 1 and 7, so we're going to need to make this equal to 6 oxygens, so we can put 3 in front. Easy as that. Alright. Oxidation of alcohol reactions. Alcohols can be oxidized by strong inorganic oxidizing agents such as potassium dichromate and potassium permanganate. Normally at this point we'd be doing that as a titration experiment, but I'm going to try and put that one together for you guys and record a video of me doing it in the lab. You will also get to see my purple hair. I have purple hair now, it's kind of weird. Alright, solutions of alcohols change to sort of blue. I think you call that a blue. It says orange to green, but that looks like a blue. Alright, alcohols can be either classified as primary, secondary, or tertiary. The rule for alcohols is that they are named according to the number of carbons attached to the carbon bearing the hydroxyl group. So here, it is attached to 1 carbon. I'm sorry, let me back up. I actually hate how this slide is explaining it. So I'm going to do this. I'm even going to draw over the top of it because it's ugly as sin. Alright, so here what we've got is this. A primary alcohol follows this pattern, which it's OH. Oh man, I am having some technical difficulties. Alright, let's try down here. So here's my OH, this is my C, and this is H and H. And off it comes my R group. This is what's known as a primary alcohol. See here we've got only 1 R group coming off the carbon that's attached to the hydroxyl, and we've got 2 hydrogens. Secondary alcohol, we're going to replace one of these hydrogens, so it becomes R, C, OH, and this is now an R group, and this is a H. And this third one, we have carbon, OH. I'm going to buy a stylus this week. R, R, and R. Alright, so now we have 3 R groups and they're all attached to an OH. Oh, let me back up. So, primary, you've only got 1 R group. Secondary, you've got 2 R groups. Tertiary, you've got 3. Now, primary alcohols are oxidized to carboxylic acid in 2 stages. What happens is we add an oxidizing agent, aka something with a lot of oxygens like chromate, and we expose the primary alcohol to it. If it, when it oxidizes, it becomes an aldehyde. When it's allowed to oxidize even further, it becomes a carboxylic acid. Right? So alcohol, leave it in the oxidant soup for forever, it becomes an aldehyde, and then when you leave it for even longer, it becomes a carboxylic acid. Now, if the desired product is an aldehyde, we can use lower temperatures and shorter reaction times to go from propanol to propanol and then the aldehyde can be distilled from the reaction mixture, so it doesn't go any further. And then here it becomes propanoic acid if we leave it too long or do not take it out. So normally this is how we used to breathalyze people. Yeah, that's how we did it. Ethanol to ethanol to ethanoic acid, and then we test. So actually, I'm just going to go back. This is essentially what we do in a titration of ethanol. Then they work out how much ethanoic acid had been created by the lack of dichromates used. So, secondary alcohols are oxidized to form ketones. This is what my body is currently making now, thanks to the keto diet. It's pretty self-explanatory. Add chromates and make it happen on the... Oh, I should probably talk about this. Whenever you see H+, this means occurs in acid. So, whenever you have anything like this, it has to be an acidified solution of chromates, or here an acidified solution of manganate. So, tertiary alcohols are not normally oxidized by heating because they're just less accessible. Here is a table. I would get it into your book. And with that, I might actually stop there. Thanks for listening. Please make sure to get to class properly on time. And with that, cheers.